In this lecture, I am going to give an introduction to the topic of duality. As far as our syllabus is concerned, this duality is mentioned in the unit number second of our syllabus. The other contents include the transportation problem and the assignment problem, which we have already studied. Now coming back to the duality. To understand duality, let me take an example of a linear programming problem. And on the screen, you can see that it is maximization problem. That is maximize z is equal to 10x1 plus 9x2. And two constraints are given. The first constraint is 3x1 plus 3x2 is less or equal to 21. And the second constraint is 4x1 plus 3x2 less or equal to 24. Okay, so this is an example of an LPP maximization problem. Let me see, let me perform some operations on these constraints. We can see that there are two constraints. I can perform some operations on these two constraints. What can I do here is I can multiply this first constraint by any number a. Okay, we can multiply the first constraint by any number a, and we can multiply the second constraint by any number b. Okay, so let me take an example here. Suppose I multiply the first constraint multiplying constraint 1 by a number that is 6. By a number that is a is equal to 6. So after multiplying this constraint by 6, what I'm going to get here is, see, I have multiplied the first constraint by 6. I will get that 6 into 3x1 plus 3x2, that is less or equal to, obviously I have to multiply both sides, therefore 6 into 21, we will get that 18x1 plus 18x2 is less or equal to 126. Okay, so this is the equation which I am going to obtain. Okay, in fact the inequality. So I haven't multiplied this second constraint by any number, but I have multiplied only the first constraint by 6. Okay, that is a is equal to 6. If I am multiplying second constraint, I will say that b is equal to something. Okay, usually we show the multiplication of the second constraint by b. So let us compare this equation comparing with objective function. The objective function is z is equal to 10x1 plus 9x2. From this inequality, from the inequality 18x1 plus 18x2 less or equal to 126, we can compare that z is equal to 10x1 plus 9x2. Now, if we compare the objective function with this inequality, we can see that 10x1 plus 9x2 is is less than, okay, it is definitely less than 18x1 plus 18x2, because x1 and x2 are positive variables. Okay, x1 and x2 are greater or equal to 0. Since they are greater or equal to 0, therefore 10x1 plus 9x2 will definitely be less than 18x1 plus 18x2. Obviously, the coefficient of x1 here is 10, here the coefficient of x1 is 18. See here, the coefficient of x2 is 9, and here the coefficient of x2 is 18. Obviously, both the coefficients will be greater, therefore this inequality 18x1 plus 18x2 is greater than 10x1 plus 9x2. So if 18x1 plus 18x2 is less or equal to 126, and we have 10x1 plus 9x2 less than 18x1 plus 18x2, therefore what we conclude here is that our objective function, therefore z will be also less or equal to 126. That is z equal to 10x1 plus 9x2. This will definitely be less or equal to 126. Okay, so what we conclude here is from this multiplication that is less or equal to 126. So what does this indicate? This indicates that 10x1 plus 9x2 cannot be greater than 126. Okay, so it should be less or equal to 126. So what is this 126? It is a kind of an upper bound or an upper estimate of the maximum value of the objective function. It means that the objective function can be less than or equal to 126. It can be 126, 125, 190, but it can't be 127, 128. Okay, it can't be any value greater than 126, but it should be less or equal to 126. Okay, it is a rough estimate or an rough upper bound or an upper estimate when we have multiplied the first constraint by the number 6. Okay, now let me change the multiplication constant. Let me say that multiply constraint 6 by constraint first by, I'm going to multiply the first constraint by, okay, 4 now in this case. Okay, first I had multiplied by 6, now I am going to multiply this first constraint by 4. That is a is equal to 4 here. Okay, I'm not multiplying the second constraint, therefore b is equal to 0. So what we are going to get here is, after multiplying this first constraint by 4, 3x1 plus 3x2 less or equal to 4 into 21. So this will be 12x1 plus 12x2. This has to be less or equal to 84. Now if we're comparing this inequality with our objective function, okay, what we are doing is comparing. Again, what can we conclude here is 12x1 plus 12x2 is greater than 10x1 plus 9x1. Okay, 9x2 in fact. Okay, see the coefficient of x1, it is 10, but here the coefficient of x1 is 12. Here the coefficient of x2 is 12, and here the coefficient of x2 is 9. Therefore, again, this inequality is greater than our objective function. Therefore, if 10x1 plus 9x2 is less than 12x1 plus 12x2, which is in turn less or equal to 84, therefore, from here we can conclude that z is equal to 10x1 plus 9x2. This should also be less or equal to 84. Now see here, our upper estimate or our bound has changed. Okay, this is our new upper estimate or upper bound of the objective function. So previously we were seeing that objective function can be 125, 120, that is the maximum value. Okay, it can be 120, 100, it can be 85, but now our upper estimate has changed. We can say that it can't be greater than 84. It has to be less or equal to 84. Okay, therefore our upper estimate has changed. Okay, it is less or equal to 84. So now it can be 83, 84, 80, 80, 70, 76. Okay, it can be any value less or equal to 84. Okay, we are interested in finding that value. Okay, our goal is to find out that value, but roughly we can say that it can't be greater than 84. Okay, so in the first step and the second step, what I have done, I have just manipulated the first constraint by multiplying it with 6 and 4 respectively. Now let me take an example of the second constraint. I can also perform some operations on the second constraint. The second constraint is 4x1 plus 3x2 less or equal to 24. Let me multiply the second constraint by 3. Okay, multiplying second constraint by 3. So let's see what we are going to get after multiplying the second constraint by 3. Since we are multiplying the second constraint, therefore we say that b is equal to 3. Okay, whenever we multiply the second constant, we multiply it with b, and the value of b here is 3. Okay, so what we are going to get here is this should be less or equal to 3 into the right hand side was 24. Okay, so I will get that 12x1 plus 9x2 is less or equal to 72. Now compare with the objective function. The objective function is z is equal to 10x1 plus 9x2. So again, we can see that although the coefficient of x2 is 9 in both the inequality and the objective function, but we can see that the coefficient of x1 in the objective function is 10, and in this inequality it is 12. Therefore, the objective function is still less than this inequality. Okay, that is 12x1 plus 9x2 is greater than 10x1 plus 9x2 because x1 and x2 are non-negative. So what we conclude here that is that if 12x1 plus 9x2 is less or equal to 72 and our objective function is less than this inequality, therefore it should also be less or equal to 72. Z is equal to 10x1 plus 9x2 is less or equal to 72. Now this is our new upper estimate. So as close we are moving to this inequality, okay, as close this inequality is moving to the objective function, our upper bound is going to reduce. Previously we had seen that our objective function, maximum value of the objective function, can't be greater than 84. Now it has further reduced it. We can't say that it will be 72, 73, 74. It can be 72 or any value less than 72, and we have to find that upper estimate. We have to find that maximum value. Okay, this is just an upper estimate or an upper bound. It restricts. Okay, it says that z max cannot be greater than 72. So if you see that so far, what I have done here is I have multiplied the first constraint by a, and I left the second constraint untouched. In the further iteration, okay, in this current iteration, what I did is I multiplied the second constraint and left the first constraint untouched. But what can we do is that we can multiply both constraints simultaneously and we can add them. So what I'm going to do here is I'm going to multiply constraint first by 3 and constraint second by 2. Sorry, constraint second by 1. That is a is equal to 3, b is equal to 1. And I'm going to add them and add them. So if we are multiplying the first constraint by 3, 3 into the first constraint was 3x1 plus 3x2, and I'm going to add it with the second constraint after multiplying it with b equal to 1, that is 4x1 plus 3x2. So this has to be less or equal to 3 into 21 plus 1 into 24. What we are going to get here is 9x1 plus 4x1, that will be equal to 13x1 plus 9x2 plus 3x2, that will be equal to 12x2. So this has to be less than 64. This has to be less than 87. 63 plus 24, it is 87. So we can perform this operation as well. Okay. Compare with the objective function. Again, what I'm going to get here is therefore our z value should also be, okay, it is another upper estimate. Okay. So now I can generalize this. What we can do to our constraints is, the first constraint was 3x1 plus 3x2. The second constraint was 4x1 plus 3x2, and I can multiply it with by any constant a, and multiply the second constant by any constant b. Okay. So if we see here, this 3a, okay, if I multiply 3a and 4b, the objective function was 10x1 plus 9x2. This 3a plus 4b, this has to be greater or equal to 10. This has to be greater or equal to this value 10. So what does this indicate? See here, this is the coefficient of x1. Okay, this 13 is the coefficient of x1. And see here, what is 3a plus 4b? 3a plus 4b will be the coefficient of x1. I have to multiply this 3x1 by a, 4x1 by b. I have to add them. Therefore, after adding, the coefficient of x1 will be 3a plus 4b. But this has to be greater or equal to 10, because the coefficient of x1 in the objective function is 10. So what we are going to get here, okay, this 13 is the coefficient of x1. It has been obtained by multiplying first by 3 and second by 1, and comparing the coefficients of x1, adding the coefficients of x1. What I am trying to do here is I am trying to get this inequality close to the objective function. Isn't it? This inequality is, I am trying to get this inequality close to the objective function. Therefore, this 13, I am trying to bring it close to 10, but not less than 10. Then I can't compare. Okay, I am trying to get this inequality close to the objective function, because if this inequality had been, if I had performed some operations to these constraints and added them in such a way that I would have got that, suppose I would have got that 10x1 plus 9x2 is less or equal to 60. What does that indicate? That indicates that after performing some operations on these constraints and adding them, I'm getting the same objective function. Okay, I'm getting the same objective function. But then I can directly say that, then I could have directly said that z max is equal to 60, because this constraint, this inequality, and the objective function we are seeing. Only then I can say that its maximum value will be 60. But see, my objective function is less than this function. Therefore, I can't say that the maximum value of z will be 87. Okay, what I am trying to do is I am trying to minimize this upper estimate. Okay, I'm trying to minimize this upper estimate. Therefore, what we have done here is I am trying to get this inequality close to my objective function. And see, the coefficient of x1 here is 13, but the coefficient of the x1 in the objective function is 10. Therefore, 13 can go maximum up to 10. Therefore, this value, this coefficient here, can't be less than 10. It has to be greater or equal to 10. It can be 10, 11, 12, 13, 14, 15, okay? But it can't be less than 10, that is, it can't be 9, because if I'm going to get an coefficient of 9, I can't compare the objective function with this inequality. Therefore, this coefficient of x1, that is 3a plus 4b, should be greater or equal to the coefficient of x1, that is equal to 10. Similarly, what can I say here is, I can say that the coefficient of x2 can't be less than 9. Okay, see here, the coefficient of x2 is 12. So if I'm trying to bring this x2, coefficient of x2, close to 9, I can at max bring it to, okay, I have to bring it at least to 9. Okay, I have to bring it to the 9. Okay, but it can't go less than 9. It can't go less than 9, because I won't be able to compare the objective function then. Okay, so how much I can reduce 13? I can reduce 13 to 10. Therefore, its maximum value will be, it's at least it has to be 10. Therefore, it can't be less than 9. Similarly, 12, I have to bring it to 9, but I can't go below 9. Okay, I can't go below 9. Here I can't go below 10. Here I can't go below 9. Therefore, the coefficient of x2, okay, we can get the coefficient of x2 is 3a plus 3b. Okay, 3a plus 3b, that has to be greater or equal to this value. 3a plus 3b has to be greater or equal to 9 in this case. Greater or equal to 9. It can't go below 9, because I won't be able to compare the objective function then. And finally, what I'm getting in the right hand side. See, what I'm getting in the right hand side is this 87. It is actually the addition of the right hand sides of the constraints, isn't it? See here, I have multiplied the right hand side of the first constraint. The right hand side of the first constraint was 21. I have multiplied it with 3. The right hand side of the second constant was 24. I multiplied it with 1, and I added them to get 87. So actually this 87, which is the upper bound, okay, which is the upper bound or the upper estimate, this is actually the addition of the right hand side of the constraints after their multiplication with some values of a and b. Okay, so what is our upper bound here is, the upper bound is, in the right hand side I had 21, here I had 24. So if I am multiplying this right hand side by a, that is plus 24 into b, this becomes now the upper bound or upper estimate. And what I have to do here is the minimization of this. I have to do the minimization of this, because I told you that the maximum value can't be greater than 87. Okay, maximum value can't be greater than 87. It can be 87, 86, 85, 80, 70, 60, but I have to find what is the upper bound. Okay, what is this upper bound? Therefore, I am actually trying to minimize this z. I have to minimize this z. To find the maximum value of the z, I have to minimize this z, because it is an upper estimate. Okay, it is an upper estimate, but obviously see here, this 13x1 plus 12x2 is less or equal to 87. My objective function is 10x1 plus 9x2. That definitely won't be 87, because 13x1 plus 12x2 will have the maximum value of 87. 13x1 plus 12x2 will have the maximum value of 87. But z cannot have the maximum value of 87, because z is less than 13x1 plus 12x2. Therefore, definitely my upper estimate will be lower. So to find the lower estimate, I have to minimize this z. Okay, I have to minimize this z. Okay, hope it is clear, because 13x1 plus 12x2 is actually less or equal to 87. Its maximum value will be 87. But the maximum value of my z cannot be 87, because the z is less than 13x1 plus 12x2. Therefore, I have to minimize this. To find the maximum value of z, I have to minimize this upper estimate. Okay, this is an upper estimate, but what is the actual this maximum value? Okay, this will definitely be less than 87. Only when this inequality and this objective function were same, then I could would have directly said that the maximum value of z will be 87. But here I have to minimize this. Okay, therefore our problem becomes of the minimization. So I have to minimize this upper estimate to find the maximum value of the z. Okay, so see here, now what does this problem become? We replace by we replace these constants by some different constants. In this case, we will replace z by w, and a will be replaced by y1, b will be replaced by y2. So I will write that minimize w is equal to 21 y1 plus 24 y2. So the problem now becomes this. Subject to the first constraint now, or the first restriction becomes 3a plus 4b greater or equal to 10. The second restriction is 3a, instead of a we'll write y1 plus 3y2 is greater or equal to 9. Y1 and y2 have to be greater or equal to 0. So this thing is known as the dual. The original problem was maximize z is equal to 10x1 plus 9x2 and the two constraints were given, but we have changed that maximization problem into the minimization problem and the two constraints are here. So this problem now is known as the dual of the original problem. So see, the original problem was the maximization problem, but its dual is the minimization problem. Now, what is the significance of these two? Let's see here. By solving both the original problem and the dual problem, okay, we will solve both the original problem and the dual problem. So if you look at the problem which I have written here, this was the original problem, that is equal to 10x1 plus 9x2 maximization problem, and the two constraints were given. So the first constraint, if I write the equation of the straight line, that will be x1 by 7 plus x2 by 7, that we have seen in the graphical solution how we write those problems. So the first constraint will be shown by this red color line because the both x1 intercept and the x2 intercept will be 7. Okay, 7 and 7. This is the straight line connecting the equation of the straight line of the first constraint. And also see here, since this is a less than constraint, so its region will be below the line. The feasible region will be below the line, and it can't go into other quadrants because the other variables are negative there. Okay, we have to be in the first quadrant because it is positive. Second quadrant, okay, or second constraint can be seen here. The equation will be x1 by 6 plus x2 by 8, that will be equal to 1. Therefore, this x1 intercept will be 6, x2 intercept will be 8, and this blue color line is the equation of the second constraint, and again the region will be below. And after seeing that, we can see that this is the feasible region. Okay, this is the feasible region. We get four corner points. This is z equal to 0. At z equal to 0 comma 0, we will get the value of 0. The objective function at another corner point 6 comma 0. Okay, you can see that 6 comma 0 is another corner point, that will be equal to 10 into 6, that will be equal to 60. Another corner point is 0 comma 7, that will be equal to 9 into 7, this will be 63. Now this is the last corner point, and this corner point will be obtained by solving these two equations. Okay, converting them into the equations and solving them, we can see that this corner point comes out to be 3 comma 4. Students know how to solve it, therefore this will come out to be 3 comma 4, and we can get that 10 into 3 plus 9 into 4. So this will be equal to 66, and we can see that the maximum value of z is equal to 66. Okay, this is the maximum value of z. So this is our optimal solution. See here again, it was not 87. Okay, neither it was 126, neither it was 72, neither it was 84, neither it was 87, but this maximum value of z was 66. Therefore, what we trying to do, we are trying to minimize the upper estimate. Our upper estimate was 126 or 84 or 72, but we were trying to minimize that upper estimate, and the minimum value of that upper estimate is 66. So coming on to this problem now, the dual problem. Now we can see that the dual is equal to minimize. Okay, this is actually dual. Minimize w equal to 21y1 plus 24y2 subject to. So the constraints are 3y1 plus 4y2. The second constraint was 3y1 plus 3y2. So first constraint, see, first constraint is, this is y1, this is y2. The intercept will be 10 by 3. That will lie between 3 and 4, because 10 by 3 is equal to 3.33. Therefore, it will lie between 3 and 4. The second intercept, that is the intercept of y2, that will be 10 by 4, that will be 2.5, which will lie here. So this red color line represents the first constraint, equation of the line of the first constraint. The feasible region should be above, because this is a greater than equality constraint. This is greater than constraint, obviously the feasible region will be above. Now seeing the second constraint, the equation of the line will be y1 by 3 plus y2 by 3, that will be equal to 1, and the intercepts will be 3 and 3. So this blue color line shows the second constraint, equation of the line of the second constraint. And again, the feasible region should be above. Okay, the feasible region should be above. So if we see the net feasible region, this will be the feasible region. Okay, this has to be the feasible region. It can't go below this blue color line, neither below the red color line. So after seeing this feasible region, we come to the conclusion that we have 3 corner points. And this is the first corner point, another corner point here, and another corner point here. Okay. So the first corner point is, suppose it is 0, 3. So the value of z at 0, 3 will be 24 into 3, that will be equal to 72. Another corner point is 10 by 3, 0. Z at 10 by 3, 0, that will be 21 into 10 by 3, that will be equal to 70. Okay, so this will be equal to 70. Now about this third corner point, we can see that the second constraint can be written as 3 and 3 can cancel out. We can get that y1 plus y2 is equal to 3. We can get that y1 is equal to 3 minus y2. Putting this in the first constraint, 3 into 3 minus y2 plus 4y2, this has to be equal to 10. 9 minus 3y2 plus 4y2, this has to be equal to 10. Therefore y2 is equal to 1. Okay, since y2 is equal to 1, y1 will be equal to 2. So this corner point here actually is 2 comma 1. So let's find out the value at 2 comma 1. So this will be equal to 21 into 2 plus 24 into 1. That will be 42 plus 24. That will be 66. Now see, the problem is of the minimization. Okay, and the minimum value is 66. So actually in the original problem, I had the maximization problem whose maximum value came out to be 66. I converted it into a minimization problem whose minimum value came out to be 66. Therefore, the original problem is known as the primal. Okay, the original problem is known as the primal. Okay, we can write it here. Original problem was a maximization problem, and it was known as primal. Okay, so what is dual problem of that? It is a minimization problem. Okay, so it is known as dual. So if the original problem is maximization, that is the primal is maximization, the dual will be minimization, and vice versa. That is, if the minimization is the primal, if the problem primal is the minimization problem, the dual will be the maximization problem. Okay, so one thing to note here is, if I consider this objective function again, maximize z is equal to 10x1 plus 9x2 subject to the constraints where 3x1 plus 3x2 is less or equal to 21. The another constant is 4x1 plus 3x2 less or equal to 24. So what could I have done here is multiply first constraint by 2 and second by 1 and add them. Okay, that is here a is equal to 2, b is equal to 1. Therefore, after multiplying this with 2, we will get that 6x1 plus 6x2. And second by 1, that is 4x1 plus 3x2, I will get that after their addition, that will be equal to 10x1 plus 6 plus 3, that is equal to 9x2. And in the right hand side, 21 into 2 is 42 plus 24, that is equal to 66. Now this is also my objective function. This is also the objective function. From here we can get that max value is 66. Definitely this will also be the maximum value of this objective function, because our objective function is z is equal to 10x1 plus 9x2. Therefore, in the previous problems, my operation on the constraints and their addition was such that it was not equal to the objective function. But here, my operation on the constraints and their addition is such that it is equal to the objective function. Here, I can directly say that the maximum value is equal to 66 because the objective function and the addition of the constraints after performing some operations is same. Therefore, actually, I can't lower this upper estimate. Okay, this is the upper estimate, but I can't lower this upper estimate. In the previous problems, my objective function was less than the addition of the constraints after some operation. Therefore, I had to lower that estimate, but here I can't lower this estimate because they are same. Objective function is equal to the addition of the constraints after performing some operations. So here I can directly say that this is the maximum value. Okay, but there Here my upper estimate or upper bound is also the maximum, but in the previous problems my upper bound or upper estimate wasn't maximum. I had to minimize my upper bound or my upper estimate. Therefore I had to minimize the problem. Therefore my dual was of the minimization problem. So hope the concept of the dual is clear. Okay, so every problem will have its dual. That is, every primal will have a dual. If the primal is a maximization, the dual will be minimization, and their optimum functions, optimum values will be same. We had seen that maximization problem had the maximum value of 66, and its dual minimization had the minimum value of 66. Okay, so let's meet in the next lecture.